There is a laboratory in California that houses a machine operating at temperatures even lower than the emptiest regions of outer space. It is not kept that cold because it is dangerous, but because the slightest interaction with its surroundings can destroy the delicate quantum state inside. That fragile condition is the reason this story is so remarkable. Quantum artificial intelligence is doing far more than increasing computing speed. It is reviving one of the deepest mysteries in modern physics, a question scientists have debated for generations. What happens before reality settles into the version we actually observe? Inside a quantum computer, the basic units of information are called qubits. Unlike the bits in ordinary computers, which can only represent either a 0 or a 1, qubits can exist in a combination of both states simultaneously. This strange property, known as superposition, allows a quantum system to explore countless possibilities at once. But the instant information escapes into the surrounding environment, that delicate state disappears, leaving behind only a single measurable outcome. Machines such as Google's Willow processor are transforming this once purely theoretical concept into working technology. As researchers continue pushing the limits of these devices, they are uncovering hints that the familiar world around us may be only a small part of a much deeper and stranger reality. The heart of a quantum computer is not an enormous mechanical engine. Instead, it is an incredibly small chip containing dozens of carefully controlled qubits. When these qubits become linked through a phenomenon called entanglement, they begin acting as parts of one larger quantum system. Rather than evaluating possibilities one after another like a conventional computer, they can represent an enormous landscape of possible solutions simultaneously. This extraordinary ability offers computational power that classical machines struggle to imitate. Yet it comes with a major challenge. Quantum information is unbelievably fragile. Even the tiniest vibration, a wandering photon, a trace of heat, or an unexpected electromagnetic disturbance can disrupt the quantum state almost instantly. That is why these processors operate inside sophisticated refrigeration systems reaching temperatures only fractions of a degree above absolute zero, conditions even colder than much of interstellar space. Under those extreme conditions, outside interference is dramatically reduced, allowing the qubits to remain coherent just long enough to perform calculations impossible for ordinary computers. For a brief instant, the processor creates an environment where quantum possibilities remain intact instead of immediately collapsing into a single answer. During that fleeting moment, the computation unfolds while multiple potential outcomes still coexist within the mathematical description of the system. The mystery behind this technology did not begin with quantum computers. It traces back to one of the most famous experiments in scientific history, the double-slit experiment. Its setup is surprisingly simple, yet its implications remain deeply unsettling. When tiny particles such as electrons or photons pass through two narrow openings without any measurement revealing which path they take, they produce an interference pattern that resembles waves overlapping each other. The result suggests that each particle behaves as though it explores multiple paths at the same time. Everything changes when scientists introduce a detector capable of identifying which slit each particle travels through. The interference pattern disappears. Instead, the particles behave as though each selected only one definite route. The striking difference is not caused by a physical barrier but by the availability of information. If no record exists revealing the particle's path, quantum behavior remains visible. Once that information becomes available, the system behaves according to the familiar rules of classical physics. This puzzle lies at the center of what physicists call the measurement problem. Quantum theory predicts experimental results with astonishing precision, yet it does not provide a universally accepted explanation for why one specific outcome emerges from many possible ones. Albert Einstein found this deeply unsatisfying. He argued that particles should possess definite properties whether anyone observes them or not. To him, the idea that reality becomes definite only after measurement suggested that quantum mechanics was incomplete. He believed hidden variables, unknown physical properties beneath quantum theory, might eventually restore a more intuitive picture of nature. Years later, physicist John Bell transformed this philosophical disagreement into a mathematical challenge. He demonstrated that if hidden variables governed reality in the classical sense, certain statistical limits would always be satisfied. Quantum mechanics predicted those limits could be violated under the right conditions. Experiments performed over the following decades consistently supported the quantum predictions. Measurements of entangled particles repeatedly exceeded Bell's classical limits, providing strong evidence that nature behaves in ways far stranger than everyday intuition would suggest. These discoveries imply that the reality beneath our ordinary experience does not operate according to the simple, deterministic rules that seem obvious on human scales. The stable world we interact with each day may emerge from underlying principles that are anything but familiar. Google's Willow processor has brought these long-standing questions into a new era. Rather than existing only as theoretical ideas discussed in textbooks, fragile quantum states are now being stabilized and manipulated inside working machines. Equipped with more than 100 qubits, improved coherence times, and significant advances in quantum error correction, Willow represents an important milestone toward practical quantum computing. Engineers are steadily learning how to preserve quantum information for longer periods while reducing the errors that naturally arise inside these delicate systems. One of Willow's most impressive demonstrations involved completing a highly specialized benchmark calculation in only a few minutes, a task that would overwhelm even today's most powerful classical supercomputers if approached using conventional methods. Although such benchmarks do not prove extraordinary claims about alternate universes or solve the measurement problem, they do highlight the remarkable capabilities of quantum computation. The mathematics works. The hardware works. The predictions match experiments with extraordinary accuracy. Yet the deeper meaning of what occurs inside a quantum computer while it performs these calculations remains one of science's greatest unanswered questions.